So hello everyone, I'm Artur. Thank you for coming to my talk. I came here from Poland, totally different time zone, so it's pretty funny to have a talk at midnight. This is me with my kiddos playing probably Zelda on our Switch. These are my socials, in case you would like to reach out to me. For the last 6 years, I've been working at Fresha. Fresha is a product company. It's a booking platform for wellness and beauty. We achieved quite an impressive scale with around 20 million appointments a month. So that generates quite a lot of interesting challenges. We have lots of cool internal tools. We care about developer experience. We have Elixir microservices, and we are always looking for new Elixir engineers. Today in my talk, I will show you how to integrate Elixir and Ruby, but using Elixir Erlang distribution protocol. And they say that communication is the foundation of every relationship. So let's see if Ruby and Elixir can be good friends. And we'll explore two approaches. The first one is rather direct. It's an implementation of the protocol in Ruby. And the other one involves an Elixir proxy that will redirect the communication to the Ruby app using port. And let's start with the first approach. But to give you some context, I will show you like the goal, what we are going to achieve. So here's I'm starting just Elixir console with Elixir in Elixir node in a distributed mode with some name. And here's my Ruby app that will connect to it. Let's see that node list is empty, so that no nodes are connected. I run my Ruby, and we can see that it's successfully connected, and they're connected. So quick summary on what Erlang distribution protocol actually is. So it's a protocol based on TCP. Its purpose is to basically allow communication between distributed nodes, and from usage perspective, it's designed in a way that all the complexity is hidden, and running something on the other node feels very, very similar to running it locally, like spawning processes and sending messages to them. The process of connecting the two nodes is called a handshake. And one more element in the whole thing is EPMD, which stands for Erlang Port Mapper Daemon, which keeps names and ports of the nodes, like a mapping from names to ports. So yeah, underneath is just TCP, but let's see how complex that is. This is a summary of an overview of the handshake. Let's go through it to give you an idea what's going on here. So node 1 first starts in a distributed node mode with some name. It registers itself in EPMD. Then node 2 wants to connect to it. So first it needs to ask EPMD for a port on which node 2 is running. Once it gets it, it establishes a TCP connection to that port and sends a message to node 2 with its name. And basically the ping pong continues. They exchange the challenges. The challenge is the purpose of the challenge is basically authentication. This is the way they prove that they know the secret value that is called a cookie. And once the handshake is complete successfully, the connection is kept open and is then used for the further communication. And TCP is basically like a pipe. You can throw a bunch of bytes on one side and read it on the other. So no data structure is imposed. So it's up to sender and receiver to prepare and interpret the data that they're sending. So each message in handshake consists of a few parts. Here is send name that you could see here, the first message sent. It consists of a few elements of a fixed or variable byte length. The first part is always size of, and it's 2 bytes. So it's very convenient to read messages this way, thanks to this field, because you can always read first 2 bytes from TCP socket. For example, it's 10, so you then read 10 next bytes from the socket. In send name, we've got a tag, which tells you that it's send name. It's a type of a message. In this case, it's send name. Then we've got flags, and flags tell the node which features, which capabilities are enabled on the given node. Basically, different OTP versions support different features. So to maintain compatibility, the nodes establish between themselves which features are allowed and can be used. So flags field contain this information. Then there's creation, which is the timestamp of creation of the node. Then the length of the name field and the name itself, which is the name of the node that is introducing itself to the other node. Yeah, all the numbers here are big endians, but we'll see that later in the code. Wireshark. It's not an advertisement of some VPN. It's a really cool tool to pick into network traffic on your computer. And what is really great about it is that it can automatically detect the type of the protocol. So here it says that it's errang distribution protocol and not just TCP with a bunch of random bytes, but RLDP. And it's able to parse the content, interpret it, and display it in a in a human readable way. So here we can see all the data, the name of the node, etc., with flags. Really useful tool for example, reverse engineering. All right, let's see the code of the solution. Here's a Ruby node class. The main part is connect node. What it does, it fetches the port from EPMD. And it does it in this way. It basically prepares the data, prepares the message, which consists of message type. In this case, it's 1 to 2. It's just a number from the documentation, and the node name. We've got a helper function here, build TCP message, which takes all of the elements in this array and packs them into appropriate format. This C means it is something that is passed as an argument to pack method, which creates a byte representation of that. And C means basically that it's of 1 byte length. And we also send a string, and it's sent just as is. So our Ruby node fetches the port from EPMD. So now it knows where the other node is running. So it establishes a TCP connection to that node. And here's the whole ping pong that you saw previously. So it builds and sends send name message. So each part of this message is prepared and formatted, also using pack. We've got fields of a different size. We've got strings. Like for example, flags is 8 byte, creation 4 byte, etc. Oh, and one more thing, we also add size of the message at the beginning, which is 2 bytes. Oh, here's an example how it looks. We get row bytes string here. Then we receive status, we receive challenge. As I previously said, we read 2 bytes from the TCP socket, interpret them as a number that is created from 2 bytes. We have message length. We read this amount of bytes. Then we get appropriate pieces. The challenge is the most interesting part, which is then used to create a digest, and digest is MD5 calculated from cookie concatenated with this challenge, and this is sent back to the node. Then that node accepts it and sends it back. Also, we also sent our challenge, which also needs to be solved by that other node. After that, we have we end up with the connection that we can use for further communication. From time to time, we need to send keep alive messages, which are just empty messages every 15 seconds to keep the connection open. And we can listen for messages. I also attempted to implement RPC call here, but it turned out to be way more challenging. Basically, a handshake is well documented in Erlang documentation. Like all the messages are explained, how to build them, what are the parts inside, all of that. In case of RPC call, it's way more complex. It involves formatting data to Erlang term format, lots of different internal details that aren't documented. But that's not all. We've got the other approach, and it's very much different approach. Basically, as software engineers, we often face some choices and decisions that we need to make. Sometimes the useful question to ask ourselves is which problem I would like to have. Maybe not like to have, but prefer to have when we have two problems. So in the approach that I just presented, the main issue was implementing the remote communication between Ruby and Elixir. And in the next approach, you will see something different. Elixir node will actually connect to another Elixir node, but it will act as a proxy and will delegate all the stuff to Ruby. So here we have to solve this part. That was our main challenge. And here, this is completely ready out of the box. And we need to take care of this communication. So here, remote communication to be solved, and here, local communication between two processes on the same host. So to achieve that, we'll use port. And port is a mechanism that allows Elixir to run a separate operating system process. So it's not a process within Erlang virtual machine, but a separate process like Ruby application, and the ways to communicate with it. And from Elixir point of view, the communication interface is done by sending and receiving messages. And from Ruby perspective, from that process perspective, it's reading and writing to standard input and output. Here's a simple example of the port. So the way it works is we open the port, which spawns Ruby process with reverse RB argument, and it sends a command to that process. This is how this application looks like. It reads from standard input. It prepares calculates some stuff and puts it into standard output. Here, after sending the command, this process this process is receiving the message. Once it receives it, it just prints it and closes the port. So we know what the port is. Let's implement the rest of the all. The full solution will look like this. We have two Elixir nodes. The proxy node will start a gen server that will manage the port. What gen server gives us is that we won't have to deal with raw message passing, so we'll have a nicer interface to deal with that. It will keep the port in its state. The two nodes will connect, and it's a regular handshake. Once they are connected, they will be able to send RPC call. The node 1 will send the RPC call to the other node, and when it will handle it, it will call gen server call, which will result in handle call, of course, and handle call will use port command. Port command will send the message to Ruby app, and Ruby will generate the result and put it into standard output. And since this will result in a message in a gen server, but since it's a regular message sent to a process, it will land into handle info callback, not handle call or handle cast. Since it's just a regular standard message. Handle call will use gen server reply so that gen server call can finish. One thing to understand here that I think is pretty important is that the communication with the port is asynchronous, while RPC call and gen server call are synchronous. So in practice, it means that RPC call is hanging and waiting for the execution to finish, and then only then it returns the value, while port command doesn't return the value, doesn't return the result. So gen server, as I said, will receive it in a handle info. So to make it all work, handle call returns no reply to keep gen server call waiting. And once it gets the message, the gen server reply is called to make the call return, and then RPC will return so that the whole flow is finished and node 1 gets what it wanted. We'll see the whole process in the code in a moment. There are a few more things that are needed to make the whole solution work. As I mentioned, instead of raw message passing, it's going to be wrapped in gen server. Port allows passing just simple strings, while we would like to have some some data structure. So I chose JSON for this job. And since the communication is asynchronous, we need some mechanism to match requests with appropriate responses. We also need something that I called here a gateway module. Basically, RPC call doesn't allow us to implement like any kind of, let's say, interceptor. We can't implement something like, I don't know, Phoenix controller to handle the request and do something about it. RPC call expects that on the other node there will be given module and function implemented, and it will be just called, and it will get the result. So we need that module in our Elixir proxy node, but it won't contain any business logic. It will just delegate the stuff to the port. We also need mimicking RPC on the Ruby side, because it will get module function arguments, and we'll need some metaprogramming to invoke given given function. Instead of single port, we'll use a pool of ports for increased scalability, and graceful error handling is always very welcomed. Okay, so let's see the code for this solution. Or actually, before the code, let's see how it works. I think to give more context. Here I'm starting distributed node with some name. Here I'm starting this Elixir proxy that will start Ruby process. And here I'm running RPC call, which takes node name, module name, function name, and its arguments. And it all goes down to the Ruby app, and the result is here. The string got reversed, but it got reversed in Ruby. Okay, so let's see the implementation. Let's start from where it all starts, so application. In application, we start, we use poolboy that starts and manages a pool of gen servers. Basically, the whole solution is pretty generic, so it could work with anything. It just takes the argument here. Okay, and what happens when I send RPC call like a moment before? We have this, let's say, gateway module that has reverse function. As you can see, it doesn't contain this business logic. It invokes this this function. And here's the gen server with its interface here. Here's a start link that starts the gen server. When starting the gen server, the port is opened with the arguments that were passed from the application. and this port is saved in the state of the Gen server, so it can be used later. We have send RPC to port function. What it does, it gets free worker from poolboy and calls Gen server call with given module function arguments. Call is, of course, handled in handle call. And what it does, it prepares a message for port, turns it into JSON string. The payload contains module function arguments, and the message also contains unique message ID, which we store in state. State keeps mapping from these messages to callers' PIDs, so that they can be so that we can later match responses with the callers. And port command is called to send this message. Let's see the Ruby part. What's going on here? Ruby reads constantly reads from standard input. When it gets a message, it parses it. It gets headers which contain that message ID. Headers just need to be passed back to Elixir. We have module name, function name, and arguments, and they are used to invoke a given module, given a function from a given module. And this module is here. It's reverse with reverse that does what it says. The response is prepared with the payload containing the result, and it's then put in standard output. And this in turn results in message in this Gen server that is handled in handle info. And sometimes it may happen that messages get concatenated because standard output buffer may not be flashed often enough. So when it happens, they are like together in one string. So we need to split them by new line, because this is the default delimiter of the messages. Each message needs to be decoded to get the structure from the JSON string. And when we get the parsed data, we fetch caller's PID from the state based on the given message ID. And then Gen server is used to send the reply with the result prepared in Ruby that we just received. We no longer need to keep those callers. We don't want the state to grow infinitely, so the message IDs and callers are removed from the state. One more thing that is happening here is that is port monitor. What it gives us is that when the port crashes, we get message about it, and it lands in handle info. And here it's handled in a way that all callers get a reply with error. Otherwise, they would just time out. But I think it's nicer to know something more what's going on and crash earlier. At this point, the port is closed, so we're opening a new one using the same argument because we can do that because it's kept in a state. And the new state is returned. Terminate callback closes the port. And that's it. You can see again how it works. All the code that I just presented is available on the repo, so feel free to check it out. If you would like to analyze it, if you would like to discuss it or give me feedback or anything, feel free to reach out to me. Here are a few resources that I find interesting related to port and to Erlang distribution protocol. So also recommended if you would like to dive deeper. So that's it for today from me. Thank you very much for coming.
Thank you. That's great. Do we have any questions? Oh, awesome.
Hi, you have it in production?
No.
Why not?
Because I just did it. I prepared it for the presentation only, but I think the second approach has potential to land on production. The first one, I think, it's pretty hard to get past POC stage. Yeah.
Soon. Better question, why don't you put it on? It's open source. You can use it. Awesome. Well, thank you again.
Thank you very much.